Alright, it's going to be Newton's Law of Gravitation, 3K, number 1. Which diagram best represents the gravitational forces Fg between a satellite S and Earth? Now, this really just follows Newton's third law, right? Newton's third law states that, well, the force of object 1 imparted on object 2 is equal to the force that object 2 exerts back onto 1. If I exert a force onto my desk, the desk exerts a force back onto me. Well, how does this law work, right? And we want to understand how this works with gravity. Well, if you think about it this way, let's say force 1, 2, it's 200 newtons, and then force 2 on 1 is also 200 newtons. All right? And so we know that force 1 on 2 is ma. Okay. Well, 200, and let's say the mass of object 2, right? Because this is force of object 1 onto 2. So the mass of 2 is, let's say it's 200 kg. And the acceleration it feels, well, that's the acceleration object 2 feels. Well, if you solve this formula, you're going to get 1 meters per second squared. 1 meters per second squared. And that's the acceleration object 2 feels because it has such a large mass. But on the other hand, force 2 on 1 is also 200 newtons. And now M1, because again, this is force of object 2 onto 1. So this is the force the object 1 feels. And so it's also acceleration object 1 feels. And so the force is still 200 again. Let's say my mass this time is much less. And the acceleration I feel, well, for this to be true, well then, divide by 1, let's actually show our work, divided by 200 divided by 1 is going to be 200, and then you get A1, and so let's call it meters per second squared. So even though my forces are the same here, the acceleration these masses feel are completely different. The acceleration that mass 2 feels, because it's mass 200, well, it only feels a very small acceleration, whereas object 1 has such a low mass that it feels such a high acceleration. It feels like an acceleration of 200 meters per second squared. All right. Now, knowing all that, knowing this is the case, well, then we can apply that to Newton's law of gravitation. Well, Mama Earth, and it's going to be Earth, and then exerts a gravitational force on the moon, and this is the moon. Well, it exerts a gravitational force on the moon, and the moon is going to exert that same force, that same gravitational force back onto the Earth. How does that happen? Because even though the Fg is the same, because the mass of the moon is so small that the acceleration the moon feels is much larger in comparison to the Earth. Earth is 200 times. Earth is around 100 to 200 times the mass of the moon. Alright? Now, and so the answer is C, if you couldn't tell. So the centers of two 15-kilogram spheres are separated by 3 meters. The magnitude of the gravitational force between the two spheres is approximately what? And so we're going to identify our unknowns. And mass 1 is 15 kg. Mass 2 is also 15 kg. And it's separated by a distance of 3 meters. Alright. And so they want to know where FG is. So set up your formula. Set up your formula. That's your formula. And so G is going to be, well, you know G. It's also on your reference table, 6.67 times 10 to the negative 11. So all you're going to do here is plug in everything. Mass 1, 15. Mass 2, also 15. R squared, so 3 squared. 15 times 15 is 225. 225. 9. And you're going to get, what's 225 divided by 9? You're going to get like 20 something? 24? 25? I think it's 25. I think 225 divided by 9. Yeah, it is 225. So, yeah, 25. So 25 times 6.67 times 10 to the negative 11. Alright. Well, that is going to give you 6. What's going to be negative 10? What's 220? What's 25 times 6.67? So you're going to get 1.67 times 10 to the negative 9. Right, 1.67 times 10 to the negative 9 newtons. And that, so the answer is C. Answer is C. 3. And you, same thing. 2 kilogram soccer balls. Alright. So mass 1, 0.425. Mass 2, also 0.425 kg. Let's actually put our units here. And the distance is 0.5 meters. Okay, 0.5 meters. And so you want to figure out your FG is, and you know what your G is, 6.67 times 10 to the negative 11. You don't really have to care about the units, because reagents, class M1, M2, R squared. 6.67 times 10 to the negative 11. 425. I'm just going to square because you're multiplying by itself anyway. 0.5 squared. Once you figure this out, 0.425 squared divided by 0.5 squared is going to give you 0.7225 times 6.67 times 10 to the negative 11. And then you're going to get 4.82 times 10 to the negative 11 newtons. Alright, so that's the answer. 4. It's actually the same thing. You're actually figuring out the same thing. You have mass 1, 7, mass 2, 7 kg. R, 2 meters, FG, trying to figure it out. What else am I missing? And G, 6.67 times 10 to the negative 11. So what do you want to find out? FG, to the G, M1, M2, R squared, 6.67 times 10 to the negative 11. 7 squared, 2 squared. Let's see, 49 over 4. It's 7 squared because you're just doing 7 times 7. So it's basically 7 squared. That is 1, 2, 25, 12.25, 12.25, 6.67, percent to the negative 11. And so that's going to be 12.25 times 6.67. And so you're going to get 8.2 times 10 to the negative 10 is that answer. And it is. It is. It's C. So the answer is C again. Damn, all the answers are C. Alright, not complaining. So when Earth and the Moon are separated by a distance of 3.84 times 10 to the 8, the magnitude of the gravitational force of attraction between them is 2 times 10 to the 20. What would be the magnitude of the gravitational force of attraction if the Earth and the Moon were separated by a distance of 1.92 times 10 to the 8 meters? So this is more of a conceptual question than a solving. Of course, you can solve it by using numbers. And I'll solve it conceptually first before I use numbers. So, in the formula is G m1 m2 over r squared. And let's say that r is 2, right? So if you square that, you get G m1 m2 4. But let's say that the question now says, well, what would be the magnitude of this gravitational force of attraction if the Earth and the Moon were separated by a distance of 1.92 times 10 to the 8 meters? Well, that's half of the original distance. It's half of 3.84. So now the new radius is 1. If the new radius is 1, well then if you're doing r squared, m2, r squared, 1 squared is going to be 1. 2 squared is 4, and that was the regular distance. The new distance is now half, because it's 1.92. And again, these numbers are hypothetical. They're not real. I'm not solving the problem right now. But this number is now less than half of the original radius. But when you square it, when you square something, you get 1 here and 4 here. 2 squared 4, 1 squared 1. And so what would the new magnitude of this gravitational force now? Well, instead of dividing by 4, which means you're quartering it, because if you divide anything by 4, let's say you divide 100 divided by 4, you're going to get 25. But here, if you divide 100 by 1, what do you get? You get 100. So what happened to this gravitational force? Well, it quadrupled 4 times. It quadrupled. So when you have r, right? When you have r, you get this. And then, well, if you divide something by 4, it's 25. But if you divide something by 1, it's 100. Well, if you divide 100 by 4, it's 25. Divide 100 by 1, it's 100. So what you're doing when you halve the radius, you're quadrupling. You are quadrupling, and that means times 4. Quadrupling your FG, your answer. And so what's times 4 of that? Well, it's going to be 8. 8 times 10 to 20 newtons. 8 times 10 to the 20 newtons. So the answer is B. But let's say you want to solve that without doing that conceptual problem. So on your reference table, there is the mass for Earth and the Moon. So you can just use mass of 1, and that will be the Earth. Mass of Earth would be 5.8 times 10 to the 24 kg. And the mass of the Moon, we'll call M2, 7.35 times 10 to the 22 kg. And so the new distance would be 0.92 times 10 to the 8 meters. You want to figure out what your FG is, and you know what your G is. And so, well, all you're doing here at this point is just plugging in the numbers. Okay, all you're doing here is plugging the numbers. And then when you plug in all your numbers, you're going to get the answer. But the conceptual method is much easier. It's much more, yeah, it's just much easier in general. Uh, hope that was helpful.